Welcome to this last class for the course called Elements of Modern Physics, and what we will be doing is we will discuss the periodic table of elementary particles, and this is very similar to what Mendeleev did for the chemical elements. And these elementary particles will be put upon some regular kind of structures, mostly hexagons or triangles, and this is called as the eightfold way. And in particular, we will talk about baryon octet, meson octet, baryon decuplet, and super multiplets. And finally, we will talk about these composition of each of these hadrons, which are the quarks. So, we will talk about 6 quarks and talk about the eightfold way of quarks. We will talk about this baryon decuplet again in terms of these quarks and the meson nonet. And finally, we will give you particle data for your so that you can store them or use them later, which will contain the masses etc., and different particles and all these elementary particles and so on. So, let me start with this periodic classification of these elements, and these are very useful and they are extremely sort of used, widely used in order to sort of make a repository of these particles, and in terms of their strangeness, their charge, and maybe even isospin, which we talk about only the bare minimum that is required for you to know that these are elementary particles, and they have a sort of arrangement which make them discernible, or they are easily identified by their charge or the strangeness number, etc. So, as I said earlier, that it's very similar to what Mendeleev did with the chemical elements, who in terms of electronegativities and ionic radii, etc., he arranged them in some kind of a table. That table has a rectangular structure, while we have here a sort of hexagonal or a triangular structure. And in particular, we will be talking about the baryon octet, the meson octet, baryon decuplets, and meson nonets, and so on. So, this is a baryon octet, and these are the moderately heavy particles are put in this honeycomb, where you see that this is neutron, proton, and the sigma plus particles, and these sigma 0 and these lambda 0, and these particles with all these 0 and minus, and then you have a sigma minus particle and so on. So, if you look at the strangeness numbers, which are noted as s equal to 0, s equal to minus 1, s equal to minus 2, and you also have these sigma 0, lambda 0 particles here, which are sort of characterized by these. So, along these slanted lines, we have charge equal to plus 1 in unit of proton charge. So, proton and the sigma plus particle, they have this charge q equal to plus 1, and then along this diagonal, where all these neutrons, sigma 0, etc., they are there. So, the charge is equal to 0, and then there are these along this slanted line, where sigma minus and this particle is there. So, there is this it is the charge is equal to minus 1, and the strangeness numbers are 0 for neutron and proton, and this middle line, the sigma minus etc., they have a strangeness minus 1, and then there is a strangeness minus 2, and these are the moderately heavy, or kind of the lightest of the baryons are placed here. So, there are 8 baryons, 6 at the corners of the hexagon and the 2 in the middle, and they according to their charge and strangeness. So, these are what it is, they are arranged like that, and the charge and the strangeness number. So, charge is q and the strangeness is given by s. So, strangeness is classified along the horizontal direction, and along the slanted lines, that is a downward slope, or you can say that it is the rightward slope. These are given by particular kind of charges plus 1, 0, and minus 1. Similarly, we will do the meson octet, but let us do a sort of summary of what we have seen. So, the particles with same charge that lie along the downward sloping line of the hexagon. This is what we said. The charge q is such that q equal to +1 for proton and sigma plus, q equal to 0 for neutron, lambda, sigma 0, and this particle which is written by this symbol, q equal to -1 for sigma minus and this minus. And similarly, the horizontal lines yield the strangeness, which is equal to 0 for n and p, and is sigma minus and sigma plus for s equal to -1 and s equal to -2 for these particles. So, this is how the baryon octet is formed, and all these lightest baryons are put along a honeycomb or hexagonal structure, and that is what is done. So, then coming to the meson octet, once again this is this is the s equal to 1, s equal to 0, s equal to -1. Now, you see that Gell-Mann actually deliberately did it instead of the octet that we saw there 0, -1 and -2. He made it symmetrically +1, 0 and -1, and these are kaons, the k0 neutral particle, k plus, pi plus and all that. You have a pi 0 and eta particle, and there is a k minus negatively charged kaon and pi minus. So, they have a charge -1, and for all these particles they have a charge equal to 0, and k plus and pi plus have charge equal to 1, and the strangeness numbers are shown as +1, 0 and -1. So, once again, you know, the horizontal line, they denote the strangeness, and the slopy lines, basically the rightward slope, they denote the charge. But this anomaly is there with the baryon octet, that s acquiring instead of these values 0, -1, -2, they take values of 1, 0 and -1. So, after 1961, so this was as we have discussed, that is Gell-Mann in 1961 he formulated this scheme, and after 61 there was a term called hypercharge was introduced, which was equal to the strangeness for mesons, and which was s equal to s for mesons and s plus 1 for baryons. But later on it was decided that the strangeness actually provides a better description, and the hypercharge was reserved for something else later on. So, it was found that the hexagons are not the only figures which are allowed by the eightfold way. There can also be triangles accommodating 10 heavy baryons. Okay, so, we have talked about the light baryons, now we are talking about the heavy baryons. And these triangular shape in which 10 heavy baryons are arranged or they are accommodated is known as the baryon decouplet. And this looks like this inverted triangle, where you have this as the sort of s equal to 0. So, this is s equal to 0, and then you have this as s equal to -1, and then you have this as s equal to -2, and this has s equal to -3, and so on. And these charges are again in this direction. So, you have a q equal to -1, and then you have along this you have a q equal to 0, and along this you have a q equal to +1, and then you have a q equal to +2. Okay. So, these are the assignments, and these various heavy baryons, delta minus, delta 0, delta plus, delta double plus, then all these sigma star minus, sigma star 0, etc. that is there in the middle, and then you have a sigma star plus, and all these other particles are there. And so, when Gell-Mann actually accommodated all these particles, and these omega minus was still not found. Okay. And it was later discovered in 1964. In fact, Gell-Mann had categorically said that he would find this particle, and he calculated the mass and the lifetime, etc., and it was later actually experimentally discovered. And this really made this eightfold way or these classification scheme to be very robust, and it is still continuing to be the classification of the elementary particles. So, all these particles were found experimentally. And so basically, after 1964, after these omega minus particle was discovered, then for the next 10 years, all the hadrons, the mesons and the baryons, they can be fitted onto one or the other multiplets, and one of the multiplet is shown where you have these kaons. So, these are the meson multiplets. So, there is a K0 and these are so medium sized particles. So, pi minus, eta, pi 0, pi plus, kaon, K0 bar and all that, and their charges are shown. So, this -1 charge. So, Q equal to 0 and Q equal to +1, and the strangeness are also indicated. So, all these particles and also the antiparticles, it is not only the particles, the antiparticles also been accommodated in these super multiplets, and there are many of them. I just show one of them here, and basically the classification of the elementary particles were complete by these 1964. So, that brings us to the Quark model, and a question that should be asked at this point, that how do these hadrons, or why do these hadrons fit into such regular and geometric patterns? Okay. Like sometimes we have a hexagon, sometimes we have a triangle, but we are able to fit everything, putting something at the middle, and this classification seemed to be complete. Okay. So, in 1964 again Gell-Mann and Zweig quite independently, they proposed that these hadrons are composed of even more elementary particles, and these are called as quarks. And the quarks actually come in 3 types, and these types are, for quarks they are called as flavors, and these quarks actually follow a similar 8-fold pattern as the mesons or the baryons. So, there are 6 quarks: up, down, charm, strange, top and bottom. So, this is written as U, and then D, and then C, and then S, then T and B. Okay. So, these are the 6 quarks. They have wide range of masses, they have fractional charge, we will see soon that they have fractional charge, and they experience all the fundamental forces of nature. So, going back to the quark picture, so there is a DUS quark. I mean this is really should be written with a small s, so it is like a small s. So, UDS, and if you put it in the vertices of inverted triangle, then the U quark has a charge which is 2/3, the S quark has a charge which is -1/3, D quark also has a charge -1/3. The strangeness number for the S quark is -1, and the strangeness number for D and U quarks are S equal to 0. Okay. So, this is what you get for the UDS: Q equal to 2/3, Q equal to -1/3, and Q equal to -1/3, S equal to 0, S equal to 0, and S equal to -1. So, that is the characteristics of these quarks. Similarly, for the anti-quarks, you can have the normal triangle, upright triangle, where we have this as S bar. So, that is the S quark with anti-quark basically. So, this 8-fold way for anti-quarks is shown. So, it is S bar, U bar, and so you have a D bar. Sorry, the D bar has to be here. And once again, the S bar and the D bar have a charge which is Q equal to 1/3, and the U bar has a charge which is -2/3. Again, the strangeness numbers are for the S bar, it's equal to S equal to 1, and for the U bar and D bar, strangeness number is equal to 0. And this is compiled in this small table. This is actually bars. I don't know why it's not seen, but anyway, these are bars. Okay. All right. So Q equal to -2/3, Q equal to 1/3, and Q equal to 1/3 for this U bar, D bar, S bar, and the strangeness number is 0, 0, and 1. Okay. So, these are the 8-fold way of the quarks and the anti-quarks. Okay. So, further there are composition rules. So, each baryon is composed of 3 quarks, and also each antibaryon consists of 3 anti-quarks. So, actually this is so the antibaryon, of course, we have not written there, but each meson is composed of a quark and an anti-quark. Okay. So, this is important. So, we actually put the charge, I mean this Q is the basically the quark. So, U quark will make a plus plus baryon with Q equal to, so this is Q, if it is not visible, this is taken from this book of Griffiths called The Introduction to Elementary Particles. It is a very, very nice book, and if you want to have a glimpse of particle physics, you can start with this book. So, you have a U quark with charge equal to 2 because each U quark has a charge 2/3. So, 3 into 2/3 will give you a 2, strangeness number equal to 0, and this is the baryon, the name of the baryon is A plus plus. Similarly, a UUD will have these Q and S values, and we have a plus, UDD is delta 0, DDD is delta minus, UUS is Z star, the Z particle, UDS is sigma star 0, DDS is sigma minus, USS is this, DSS is that thing, and S equal to SSS is this particle that is there. So, all these particles are, the baryons are listed, and their quark compositions are listed as well. And you have a meson on it as well. So, there is a UU bar and a UD bar, then the DU bar. So, UU bar makes a pi 0 meson, and then you have a UD bar which makes a pi plus. So, this is pi plus, and then you have a DU bar which makes a pi minus, then eta particle, then kaons which are US and so on. So, if you write it is like US, then DS bar, SU bar, etc., all these kaons are there. Interesting that this does not have any analog, in the sense that SS bar, the total charge is 0 and the total strangeness is 0, and it is not known. So, this way the baryons and the mesons they also can be described in terms of the quarks. And finally, I give you a list of particle data, it is only for your record. So, these are leptons of spin half, so these like electrons and neutrinos and so on. The charges are given and the masses are given as well. So, masses are in MeV. So, there is the mu meson and then neutrino and then tau neutrino and so on, and their masses are given in MeV. Electron is of course the lightest, and then you have muons and mu neutrinos have neutrino has no mass. So, that is mass is 0, and muon has a mass which is 105 MeV. Tau is really heavy, which is 1777 MeV nearly. So, these are quarks with spin half. So, we have a down up strange term bottom top with the charges minus 1/3, 2/3, minus 1/3, 2/3, minus 1/3, 2/3. And as we have said earlier that their masses vary widely, it goes from 7 MeV to 17,400 MeV. That is a large variation in the mass. Then these mediators of force which are spin 1 mediators, the mediators of strong force, they are called gluons, just like the mediator of electromagnetic force is called as photon. So, these are strong forces called gluons which have charge 0. So, these are charge neutral objects and mass is also 0. Electromagnetic is of course photon with no charge and no mass, just like gluons. And the weak has for the W plus minus charge, it is a charge plus minus 1 with a mass which is 80.4 MeV, and Z0 again a neutral particle charge 0, but mass is equal to 91.19 MeV. So, these are the mediators spin 1. Then there are these baryons which we have talked about, this proton, UUD, charge is equal to 1 and mass is known to be 940, close to 940 MeV, 938.27. Similarly, neutron is UDD, charge 0, 939.56, almost same as that of proton, lambda particles and so on and so forth, UDS, and these are the masses that are given. So, there is only data, you can store them, and if there is any question on this, you could refer to this table that is there. So, all these particles and their quark content or the composition is mentioned along with the charge and the mass. So, finally, the baryons, which are high spin baryons, the spin is not half, but the spin 3/2 baryons such as delta particles. We have not talked about the spin or the isospin, but just presenting it still in data. So, delta is UU, UUD, UDD, DDD, and each come with a charge. So, 3 U's will have 2 charge equal to 2 in the unit of proton charge, and then you have a UUD which has a charge 1, UDD has charge 0 and DDD has charge -1 and so on. Yeah, so then there are the sigma star particles which are 1 0 -1 for these USS, DSS, sigma minus is SSS and so on. Then there are pseudoscalar mesons which are, so these are lighter particles or intermediate particles. So, we have a pi meson, pi plus minus meson, pi 0. They are formed by the combination of this, and you see that they are combinations of quark and anti-quark with a variety of charges and masses and so on. And the vector mesons which are spin 0, so that they are rho, k star, omega, psi, d star and these gamma, and so these are spin 0 things and with their quark contained is shown. And that is precisely the course is all about. And if I try to give you a final overview of course that we have done so far, we have started with so summary of the course. We have started with classical mechanics, in which we have talked about a little about Newtonian mechanics and Lagrangian mechanics, and then we have talked about relativity as well. So, we have a special theory of relativity which was briefly discussed, and Lorentz transformation equation etc. were told. Special theory of relativity, in which we found that in very large velocities the space and time are coupled. Then we have talked about these quantum theory, the development of basically quantum mechanics, that is what led to the formulation of quantum mechanics and so on. So, we have talked about quantum theory, and then we have talked about quite elaborately on quantum mechanics. We have done a lot of problems on barrier transmission, hydrogen atom, harmonic oscillator and so on, and we also have done perturbation theory, and we have done which are called as the approximate methods when you cannot solve the Hamiltonian exactly. We have done that. Then we have done also electromagnetism, in which we started from these electrostatics and magnetostatics and have landed up with the Maxwell's equations, and various boundary conditions have been discussed. Then we have done statistical mechanics, in which all these ensembles and the 3 distributions, namely the Maxwell-Boltzmann, Bose-Einstein and Fermi-Dirac distributions are discussed. Then we have done solid state physics, and this solid state physics comprises of a little bit of crystal structure, and then we have done these phonons and the free electron theory, and some results which are of importance at this level, they have been discussed. So, solid state physics, then we have done nuclear physics, in which we have talked about structure of the atom, radioactivity, etc. So, we have done nuclear physics as well. So, all these more or less, apart from quantum mechanics where we have spent about 3 weeks or so, other than that most of these we have either spent a week or 2 weeks or a week and a half and so on. And then finally, we have done briefly relativistic quantum mechanics and particle physics. Relativistic and particle physics. So, the course really ends here, and where these are really the elements of modern physics, which means that we have picked up each one of the topics that constitute modern physics and have tried to justify as much as we could do in 1 week or 2 weeks or even 3 to 4 weeks. I mean, quantum mechanics, even if we have spent say 3 to 4 weeks, that's not enough. One needs to have a complete course on that, but I've tried to cover and touch upon the ones that are of utmost importance and one should know. And if you supplement this course material by the problems that will be given for the homework or the assignments, then you would know what these this modern physics course is all about. There are books on modern physics, a number of them. We have Crane and we have Beiser and we have many other books which are really good, and one should also take a look at that. They are probably more elaborate for most of these topics, but at least the bare minimum along with the ones that are of importance in learning the subject that have been given. So, I will stop here, thanking each one of you for attending the course and benefiting from it. It will be a pleasure to hear more about the course and where you want me to improve, or if some concepts and fundamentals have not been cleared, I will be most happy to answer. Thank you very much.